Hidden inside a tiny dwarf galaxy, a black hole named IC10 X-1 defies what we thought was possible, heavier than theory allows, and spinning faster than expected. What makes this cosmic giant so extreme? Tonight, we'll explore its mysteries together. If you enjoy these journeys, please like, subscribe and share, and tell us in the comments, do you think black holes like this could exist even closer than we realize? Thank you for watching. Now, let's begin. Across the quiet fabric of the local group galaxies drift in mutual orbit like faint lights scattered across dark water. The Milky Way lies at the center of this small collection, accompanied by the large and small Magellanic Clouds, Andromeda to the north, and Triangulum further away. Between and beyond them hang dozens of lesser companions, dwarfs of irregular form, dim and dusty, some no larger than the Milky Way's brightest clusters. In this subdued neighborhood, gravity holds a delicate balance. Each system moves not in isolation, but as part of a loose gravitational weave that binds them to the shared center of mass of the local group, a space roughly 10 million light-years across. The distances between galaxies are vast but not empty. Streams of hydrogen gas stretch invisibly through the void. Clouds of dark matter unlit but massive form the unseen scaffolding that keeps the group together. Within this region, quiet interactions are constant. Galaxies pull at one another, reshaping their gas and triggering the birth of stars. It is an environment of soft motion and ancient inertia, where even the smallest dwarf galaxy can harbor events of extraordinary power. From a vantage point on Earth, this collection of galaxies appears scattered against a background of fainter and far more distant systems. Astronomers divide the sky into constellations to anchor their view, and within the modest figure of Cassiopeia lies one of these faint neighbors, a compact irregular dwarf known as IC10. Its light crosses roughly 2.5 million light-years to reach our telescopes. On that journey it is weakened by intervening dust in the Milky Way's plane, which lies directly in the line of sight. What remains when it arrives is a soft haze easily lost among brighter stars, so that the galaxy's existence is only confirmed through careful imaging and spectral observation. Despite its obscurity, IC10 occupies a remarkable place in the local group's ecology. It is one of the very few known starburst galaxies within this volume, small in size but extraordinarily active in forming new stars. In a region otherwise subdued where most dwarf galaxies show signs of age and exhaustion, IC10 burns with youth. The gas within it has been compressed into dense knots where gravitational collapse proceeds at high efficiency. These regions radiate strongly in hydrogen emission lines, signifying clouds of ionized gas lit by newly formed massive stars. Such bursts of star formation do not last long in cosmic terms, yet during their brief duration they shape the galaxy's entire chemical and energetic landscape. They enrich its interstellar medium with heavier elements, produce powerful winds, and stir its gas into chaotic filaments. For astronomers studying stellar evolution, this makes IC10 a natural laboratory, a compact nearby stage on which processes typical of more distant and massive starbursts can be observed with relative clarity. The local group itself offers an ideal framework for comparison. While Andromeda's population of stars is largely mature, and the Milky Way's own formation rate steady and moderate, IC10 represents a more extreme phase. Its small gravitational potential allows gas to collect and ignite in waves rather than settle into stable rotation. The result is a galaxy that flickers in activity, alternately consuming and replenishing its reservoirs of gas through inflows and outflows. Observations in the radio and infrared reveal that its gas envelope extends far beyond its visible boundary, forming a faint halo of material likely acquired through earlier interactions. This environment, though modest in scale, can give rise to some of the most massive stars known. Each such star lives only a few million years before collapsing or exploding, but during its short existence it floods its surroundings with ultraviolet radiation and high-speed winds. The cumulative effect of many such stars is to sculpt the interstellar medium into cavities and shells, setting off secondary waves of compression that trigger further star formation. In IC10, these processes are visible as intricate knots of emission arranged in irregular arcs. Within them lie clusters containing dozens of massive O-type stars, luminous enough to rival entire stellar populations in older dwarf galaxies. When these clusters are studied through spectroscopy, their light reveals a metallicity lower than that of the Milky Way. This difference matters profoundly. A low metallicity environment allows stars to retain more of their mass, since reduced metal content leads to weaker stellar winds and slower mass loss. Consequently, the massive stars in IC10 can end their lives as heavier remnants neutron stars or black holes of unusually high mass. Thus, from the quiet spread of the local group emerges a paradox. Within one of its smallest and most obscured members, gravity and gas have conspired to produce conditions favourable to forming extremely massive compact objects. These are the same conditions that in the early universe may have seeded the first generations of black holes. The presence of IC10 so near the Milky Way therefore provides a unique window into processes that were once more common at higher redshift. What can be observed here with modern instruments may mirror what shaped galaxies billions of years ago. Telescopes tuned to multiple wavelengths bring this faint dwarf into focus. In optical light, its irregular outline resembles a smudge. In the infrared, dense star-forming knots shine through the dust. In radio wavelengths, maps of neutral hydrogen trace the swirling motions of gas that feed its central regions. High-energy observations in turn reveal bright points scattered across the field signatures of X-ray sources within the galaxy. Among them, one stands out for its periodic intensity and deep eclipses a compact binary known as IC10X-1. Its discovery would come to define much of what makes this galaxy significant to modern astrophysics, but at this first step the focus remains on the landscape that hosts it. Viewed as part of the local group IC10 occupies a transitional place both geographically and chemically. It lies near the boundary between the Milky Way's immediate domain and the outer reaches of Andromeda's influence. Its gas composition reflects that intermediate status, modest metallicity compared with the Milky Way but richer than the most primitive dwarf companions. The galaxy's shape is irregular with faint arms of gas and star clusters extending unevenly from its centre. Its rotation is slow, its structure chaotic, yet its internal brightness betrays intense ongoing formation. The very fact that such a small system can sustain this level of activity suggests that tidal interactions or inflows of gas from the intergalactic medium have recently replenished it. In a universe where most small galaxies gradually fade, IC10 remains luminous with change. Seen from Earth through layers of interstellar dust, it is both present and hidden, its light reddened and attenuated. Astronomers studying it must correct for the heavy obscuration caused by the Milky Way's own dust lane. Yet the challenge only deepens the intrigue. When those corrections are applied, the galaxy's intrinsic luminosity emerges stronger than expected, confirming its starburst status. Its surface brightness in hydrogen alpha emission corrected for extinction rivals that of much larger systems. The local group once thought to be a quiet backwater of cosmic evolution, thus contains within it a pocket of remarkable vitality. Every observation of IC10 reminds astronomers that the universe's dynamism does not depend on size. A dwarf galaxy can serve as both an archive of early conditions and a stage for present extremes. In its clouds of gas and clusters of blue-white stars, the forces that build and destroy continue to act on scales both vast and microscopic. The local group's calm frame becomes in this corner a landscape of sudden brilliance, a reminder that even near home the cosmos still holds worlds of violent creation hidden beneath quiet light. In the quiet hierarchy of the local group, IC10 appears modest, yet its interior tells another story. It is classified as a dwarf irregular galaxy, a system that lacks the ordered symmetry of spirals or the compact shape of ellipticals. Instead, its stars and gas form loose knots and filaments that stretch across a few thousand light years. Within that small volume, turbulence replaces structure. Gas flows or uneven dust thickens in one region and thins in another, and young clusters emerge wherever gravity and density momentarily cooperate. It is a galaxy in constant flux where each generation of stars reshapes the conditions for the next. Though its total stellar mass is only a fraction of the Milky Way's, its rate of star formation per unit volume is many times higher. This intense activity classifies it as a dwarf starburst galaxy, one of the nearest examples of that rare and energetic type. The reason for this compact blaze lies partly in the gas that fills IC10's interior. Unlike larger galaxies that have settled into rotational equilibrium, IC10's gas remains dynamically disturbed. It likely absorbed fresh material from its surroundings, perhaps stripped from a passing neighbour or drawn in from the intergalactic medium. That inflow may have compressed older gas reservoirs, igniting a surge of new stars. Spectroscopic surveys of the galaxy's neutral hydrogen reveal velocity gradients and twisted flows signs that it is not rotating smoothly, but instead experiencing internal collisions between gas clouds. These collisions can trigger gravitational collapse, leading to bursts of star formation. The result is a small galaxy glowing far beyond expectation for its size. The low metallicity of IC10 adds to its unusual nature. Metallicity in astronomical terms refers to the abundance of elements heavier than helium. In galaxies with low metallicity, stellar winds are weaker, because heavy elements contribute to the opacity that drives those winds. With weaker winds, massive stars lose less mass during their short lifetimes, allowing them to die heavier and leave behind more massive remnants. IC10's starburst phase therefore produces an outsized number of massive stellar remnants, including black holes of significant mass. This relationship between environment and stellar fate makes IC10 an important target for understanding the kinds of galaxies that once populated the early universe. Many of those early systems were small, irregular, and metal-poor, much like IC10 today. At optical wavelengths, the galaxy's true brightness is masked by heavy extinction. It lies almost in the plane of the Milky Way, where thick layers of dust and gas obscure much of the view. To penetrate that screen, astronomers use infrared imaging and radio observations. In those wavelengths, the hidden structure of IC10 appears with greater clarity. Bright star-forming regions dot its disk, concentrated toward a central zone where gas density is highest. Infrared maps reveal clusters so young that their stars are still partially embedded in their natal clouds. Some of these regions are compact and luminous, resembling miniature versions of the massive clusters found in the Milky Way's inner arms. Beyond the optical and infrared, the radio spectrum paints another picture: diffuse emission from synchrotron radiation produced by electrons spiraling in magnetic fields. This glow marks the presence of cosmic rays accelerated by supernova explosions. In IC10, the radio brightness per unit star formation rate is unusually high, suggesting that many supernovae have occurred in the recent past. These explosions inject energy into the interstellar medium heating gas, and driving winds that extend beyond the visible boundaries of the galaxy. The combined action of stellar winds and supernova shockwaves pushes matter outward, sometimes escaping the shallow gravitational potential altogether. Yet even as some material is lost, other inflows replenish it, maintaining a delicate cycle between loss and renewal. Within this turbulent scene, certain areas burn brighter than others. The most luminous of these contain populations of massive stars at the end of their lives, Wolf-Rayet stars. These are rare evolved stars that have shed their outer layers, exposing hot, dense cores that blow powerful winds. In the Milky Way, such stars are uncommon. In IC10, they are numerous. This overabundance signals that a recent episode of massive star formation has occurred. Surveys count more than 100 confirmed or candidate Wolf-Rayet stars within the galaxy, an extraordinary number for its modest size. The presence of so many indicates that the starburst is both recent and vigorous, since these stars live only a few 100,000 years before collapsing. Each Wolf-Rayet star contributes to the galaxy's energy budget through its wind. These winds travel at thousands of kilometers per second, colliding with surrounding material and creating shock fronts that emit in X-rays and ultraviolet light. Overlapping winds from multiple stars carve superbubbles in the interstellar medium, which later become the cavities from which new clusters emerge. In IC10, many of these bubbles have been mapped in emission lines of hydrogen and oxygen, forming an intricate pattern of shells and filaments. These structures trace the interaction between intense stellar activity and the fragile fabric of the galaxy's gas. The Wolf-Rayet population of IC10 is also notable for its composition. In metal-rich galaxies, most such stars are of the carbon sequence type, showing lines of carbon and oxygen in their spectra. In IC10, the ratio between nitrogen-type and carbon-type Wolf-Rayet stars is unusually high. This reflects the low metallicity environment where stars evolve differently and retain their outer hydrogen layers longer. These details, extracted from spectral studies, help refine models of stellar evolution under conditions similar to those in early cosmic history. For scientists, IC10 is more than a nearby curiosity. It is a living analogue of galaxies that existed when the universe was young and heavy elements were still scarce. The environment shaped by these stars is not only luminous but also unstable. The feedback from winds and supernovae compresses nearby gas in some regions while dispersing it in others. The result is a patchwork of dense molecular clouds and expanding cavities. It is within such a landscape that compact objects form neutron stars and black holes born from the deaths of massive progenitors. Many of these remnants remain bound to binary companions, creating systems that emit X-rays as matter is drawn from one star to another. It is within this population that the system later known as IC10 X-1 was discovered. At this stage in the narrative, the galaxy itself remains the subject, not the single source that would later define it. The emphasis lies on how a small irregular system can host the extremes of stellar life and death. The conditions of IC10, a dense supply of gas-low metallicity, and abundant massive stars make it an ideal environment for creating heavy black holes. Each generation of stars enriches the gas slightly, but the overall metallicity remains low enough to sustain continued formation of massive remnants. This feedback cycle can persist until the gas reservoir is depleted or expelled. The galaxy thus represents a snapshot of a transient but crucial stage in galactic evolution. The scale of IC10's energy output contrasts with its modest mass. Measurements of its total infrared luminosity indicate that despite its small size, it produces energy comparable to much larger spiral galaxies. That luminosity arises from dust heated by young stars and re-emitting in the infrared. In the ultraviolet IC10 glows intensely, while in X-rays it shows numerous point sources and diffuse emission. Each of these wavelengths reveals a different layer of the same process, the transformation of gas into stars, and the eventual return of matter to space through stellar death. The entire system operates as a compact, self-contained engine of creation and destruction. Seen from afar, IC10 might appear insignificant next to the grand spirals of the local group, yet its importance lies precisely in its scale. It offers astronomers a nearby example of the environments where the universe's first massive stars likely formed. Its ongoing starburst, though small in absolute terms, mirrors conditions once common in young galaxies. From the outer perspective of the local group, IC10 stands as a microcosm of early cosmic behavior. Its irregular light filtered through the dust of the Milky Way continues to reach Earth as a faint signature of enormous activity, carrying within it the clues to how the smallest galaxies can harbour the heaviest of objects. To study IC10 is to look through a veil that lies between the stars of the Milky Way and the wider universe beyond. The galaxy hides behind a thick curtain of interstellar dust near the galactic plane, where countless microscopic grains absorb and scatter visible light. Through optical telescopes, its image appears dim and irregular, faint knots of red hydrogen. Emission, loose sprays of young stars and uneven patches of brightness that seem to dissolve into the background. For decades, astronomers debated its shape, distance, and even its type because the data were blurred and incomplete. What they saw was not the galaxy itself, but a distorted reflection. Its blue light stripped away its outlines, softened its colours, turned copper red by the dust that lies between. Only with careful correction for extinction and the use of longer wavelengths does its hidden brilliance begin to emerge. Once the light is restored to its true balance, IC10 reveals itself as one of the most active dwarf starburst galaxies in the local group. The obscuration toward this region of sky is unusually severe. Several magnitudes of visible light vanish before it reaches Earth, absorbed by the thick molecular clouds of the Perseus arm. In visible light, the galaxy's central regions are almost invisible, but in the infrared they shine with intensity. Infrared wavelengths pass through dust more easily, and so astronomers turn to specialized instruments capable of capturing that deeper glow. Observed this way, the faint smudge of earlier photographs becomes a field of vibrant clusters, each rich in hot young stars. In the far infrared, still longer wavelengths reveal the re-emitted energy of warm dust grains, mapping where stellar radiation is strongest. These observations draw a clear pattern, concentrated cores of heat and light, surrounded by diffuse envelopes of gas. The view changes again in radio wavelengths, where neutral hydrogen outlines vast arcs and filaments, extending well beyond the visible galaxy. Together these wavelengths combine to form a composite image that captures both the hidden and the revealed layered structure of a galaxy in motion. The apparent disorder of IC10 begins to make sense when these different views are combined. Its uneven brightness is not only a matter of internal turbulence, but also of foreground interference. Dust lies thicker in some directions than others, allowing a few windows of transparency through which astronomers can glimpse deeper layers. After correcting for this patchwork of extinction, a subtle organization appears: a slow rotation, a loose disk, and a series of lopsided clusters that hint at past interactions or external gas infall. The galaxy may once have drawn material from a smaller companion, or from the intergalactic medium events that can compress gas and ignite a wave of star formation. What looks at first like chaos is in truth the record of past collisions and present renewal. The foreground of the Milky Way complicates matters further. This same dust that hides the galaxy also fills the field with stars from our own system crowding the view. Many early observers mistook its bright points for foreground objects, unaware that some belong to a distant system beyond. Only with careful photometric measurements comparing colour motion and brightness did astronomers begin to separate the local from the external. Space-based infrared telescopes provided the breakthrough. Freed from atmospheric interference, they detected the galaxy's full radiance, revealing a compact but energetic system whose luminosity far exceeds what its size would suggest. In total power output, this small galaxy rivals much larger spiral systems despite containing only a fraction of their mass. Spectroscopy adds another layer of understanding. When its light is dispersed into a spectrum, it reveals a chemical fingerprint different from that of the Milky Way. The metallicity of IC10 is distinctly low, meaning it contains fewer heavy elements relative to hydrogen and helium. This is a crucial factor in its evolution. In such environments, stellar winds are weaker, allowing massive stars to retain more mass until they collapse. The result is an abundance of heavy stellar remnants, neutron stars and black holes, larger than those produced in metal-rich galaxies. In this way, IC10 provides a living model of conditions thought to prevail in the early universe, when the first galaxies were forming and heavy elements were still rare. Observing it allows astronomers to study not just a small companion of the Milky Way, but an echo of the distant past written in nearby space. The measurement of distance under these dusty conditions presents another challenge. Among the most reliable methods are Cepheid variable stars whose brightness rises and falls in a precise rhythm tied to their intrinsic luminosity. Observed in the near-infrared, where extinction is weaker, they provide accurate distance estimates. Using these natural beacons, astronomers place IC10 at roughly 2.5 million light-years from Earth, securely within the bounds of the local group. This proximity makes it an extraordinary laboratory, close enough to resolve individual clusters and even bright stars, yet far enough to represent a distinct galactic environment. Infrared surveys reveal that beneath the current blaze of young stars lies an older population. Red supergiants and asymptotic giant branch stars trace earlier bursts of star formation, showing that the galaxy's history is one of repetition rather than singular eruption. Each cycle enriches the interstellar medium slightly, but not enough to erase its primitive character. The current phase is particularly intense, fueled by dense reservoirs of gas and driven by the cumulative effects of previous generations. Ultraviolet radiation and strong stellar winds now dominate the central regions, sculpting clouds into cavities and filaments. Within those cavities, pressure fronts compress gas, further setting the stage for new clusters to form. The system thus maintains its own rhythm, formation, feedback and renewal. Radio maps extend the story outward. They show neutral hydrogen flowing beyond the optical boundaries, shaped into arcs that suggest past supernova explosions or large-scale gas outflows. Embedded within these envelopes are compact molecular clouds, dense pockets of carbon monoxide emission that mark the future sites of starbirth. The turbulence inside these clouds indicates the influence of earlier generations of stars whose winds and shocks continue to stir the medium. In this balance of destruction and creation, the galaxy sustains its vitality. The dust that obscures its light is both a record and a participant in that cycle. Grains of carbon and silicate formed in the atmospheres of evolved stars or expelled by supernovae seed the next wave of molecular clouds. Even in a low metallicity environment, this process advances rapidly under the pressure of a starburst. To understand its luminosity, astronomers must measure across the entire electromagnetic spectrum. Visible light captures only a small fraction of the energy. The rest is absorbed by dust and re-emitted in infrared. When the data from all bands are combined, the true scale of its output becomes clear. IC10, though small, radiates as much infrared power as galaxies hundreds of times its mass. Most of this light comes from a few concentrated clusters where massive short-lived stars flood their surroundings with ultraviolet radiation. The hydrogen gas around them becomes ionized, forming bright nebulae that glow even through the dust when seen in narrow spectral lines. These compact sources dominate the galaxy's appearance in high-resolution images, giving it the texture of scattered embers burning in a fog. Each portion of the spectrum tells its part of the story. Ultraviolet light reveals the newborn stars that energize the gas. Infrared observations show where dust absorbs that energy and releases it again as heat. Radio signals trace the cold hydrogen that will soon form the next generation of suns. Together they form a continuous narrative of a galaxy caught in the act of transformation, modest in size yet immense in energy. The contrast between what is visible and what is concealed defines its nature, a dwarf system of quiet appearance and violent interior life. Within the galaxy's crowded heart, the cycle of birth and destruction continues without pause. Clouds of gas compress under gravity, ignite into brilliant clusters, and then are torn apart again by the very stars they create. This compact region is where energy is concentrated most intensely, where ultraviolet radiation, stellar winds and shock fronts reshape the interstellar medium on scales of light years. The rhythm of activity here defines the character of the entire system, a small galaxy that glows with the strength of something much larger. In these dense nurseries, the most massive stars form, quickly burn fiercely and live only briefly before collapsing in supernova explosions. The continuous churn of energy sustains a state of near-constant renewal. Every few million years another generation rises, filling the same cavities once cleared by its predecessors. The environment of IC10 is dominated by clusters of such massive short-lived stars. Among them are the Wolf-Rayet stars, luminous beacons at the end of stellar evolution. They represent an advanced phase of life for the heavier Sun's objects that began with more than 20 times the mass of our Sun and have already lost much of their outer hydrogen layers. Their cores are exposed and the winds streaming from their surfaces move at thousands of kilometers per second, filling surrounding space with ionized gas. Each of these stars can eject mass equivalent to Earth's entire volume in minutes. Collectively, they carve bubbles of low density into the interstellar medium, producing the irregular network of filaments seen in hydrogen and oxygen emission. In IC10, the number of known or suspected Wolf-Rayet stars is extraordinarily high for such a small galaxy. This population stands as one of its defining features and the clearest sign of how active its current starburst truly is. Through spectroscopic analysis, astronomers can identify which types of Wolf-Rayet stars dominate. In galaxies with high metallicity, the carbon sequence types are more common. Here, however, nitrogen-type stars prevail. The balance between the two gives insight into how stellar evolution behaves in low metallicity environments. The nitrogen-rich variety signals that the outer layers of these stars are not lost as quickly as in more metal-rich systems, allowing deeper fusion products to remain hidden until later stages. This difference alters the way massive stars die and determines what kind of remnants they leave behind. The abundance of nitrogen-type stars in IC10 implies that its conditions resemble those of galaxies formed in the early universe, where heavier elements were still scarce. Observations reveal that these powerful winds do more than sculpt their surroundings. They also influence the galaxy's chemical future. The material expelled from Wolf-Rayet stars enriches the surrounding gas with helium, carbon, nitrogen, and oxygen elements necessary for later planetary systems. Yet this enrichment competes with the removal of gas itself, since the winds can blow large fractions of material beyond the galaxy's shallow gravitational hold. The struggle between retention and loss determines how long the starburst can continue. In IC10, signs of outflow are visible in the extended filaments of ionized gas that stretch far beyond its optical limits. Such features indicate that energy from clustered stars is driving a galactic-scale wind. Even as this wind removes material, new clouds condense in its wake, maintaining a delicate equilibrium between escape and renewal. The combined radiation from these young stars is immense. Ultraviolet photons stream outward, ionizing hydrogen clouds that glow in soft crimson light. These emission regions form the visible traces of the galaxy's most active zones. Embedded within them, stellar clusters pack hundreds or thousands of suns into regions only a few light-years wide. Their gravity binds them tightly, but the pressure from their own radiation pushes outward, eroding the dense envelopes that once sheltered them. Infrared maps show shells of heated dust surrounding these clusters, while X-ray observations reveal the aftermath of supernovae within them. Each wavelength contributes to a single story, the continuous recycling of gas into stars and back again. The formation of such clusters depends on the balance between cooling and heating in the interstellar medium. Cold molecular clouds collapse under gravity only when they can radiate away energy efficiently. Yet as soon as new stars appear, their radiation begins to warm and disperse, the gas halting further collapse nearby. This self-regulation gives rise to the patchwork of active and quiescent regions across the galaxy. Where older clusters have cleared the gas, new ones cannot form until fresh material drifts in. In IC10, the high density of gas and the constant turbulence caused by winds and supernova shocks ensure that new material is always being reshuffled into dense pockets. These become the sites of the next generation of stars, perpetuating the burst-like rhythm that defines the system. Astronomers studying this cycle often turn to the ratio of star-forming mass to total gas mass as a measure of efficiency. In most dwarf galaxies, that ratio is low. In IC10, it is remarkably high. The galaxy is converting its gas into stars at a rate that, if sustained, would exhaust its reserves within a few 100 million years. Such timescales are brief in cosmic terms, suggesting that the current phase is transient. At some point, feedback from massive stars will blow out or heat the remaining gas, to the point where formation ceases, leaving behind an aging population of remnants. But for now, the balance still favors creation. The visible result is a compact galaxy whose infrared luminosity rivals much larger systems powered by the brief but brilliant lives of its most massive stars. Within the galaxy's central regions, radiation pressure and gravity interact in complex ways. The most massive clusters generate intense photon fields that repel dust and gas, driving it outward in expanding shells. Where these shells collide, they compress material into new condensations. The process acts like a self-sustaining chain reaction, with one burst of star formation triggering another nearby. Radio and infrared maps show concentric arcs around several of the brightest clusters, evidence of such cascading waves of formation. These arcs trace the mechanical feedback of stellar winds on galactic scales, forming a dynamic landscape where creation and destruction proceed simultaneously. The metallicity of the gas also shapes the appearance of these regions. With fewer heavy elements to absorb and re-radiate light, the gas cools less efficiently, and the resulting stars are generally hotter and more luminous than their high metallicity counterparts. This contributes to the extreme brightness of IC10 in the ultraviolet and infrared. It also means that the black holes formed from such stars may reach greater masses. In this sense, the current phase of activity is not merely a transient phenomenon, but a potential origin point for the compact objects that will define the galaxy's future. When viewed together, the physical processes at work in this dwarf galaxy, winds, radiation, turbulence, and collapse, form a self-contained laboratory of stellar evolution. In the space of a few thousand light-years, nearly every stage of the cosmic cycle is visible at once: molecular clouds, forming stars shaping their environment, and remnants returning energy to the interstellar medium. This concentrated activity compresses the evolution of an entire galactic disk into a region small enough to study in detail. For researchers seeking to understand how the earliest galaxies built their heavy elements and their first black holes, IC10 remains one of the most accessible analogues. Its brilliance, however, is temporary. Over millions of years, the gas supply will dwindle, the ultraviolet glow will fade, and the cavities will expand into empty space. The dwarf galaxy will settle into a quieter phase, its remaining stars cooling and aging. Yet even then, the legacy of this epoch will endure in the heavy elements now scattered through its gas, and in the compact remnants, neutron stars, and black holes that orbit unseen among the clusters. These remnants will persist long after the last bright star has faded, silent witnesses to the brief period when a small dusty system outshone galaxies many times its size. Among the crowded fields of luminous clusters and glowing nebulae, one population stands out for both its rarity and its importance: the Wolf-Rayet stars that dominate the late stages of massive stellar evolution. These objects, scattered through the densest regions of the dwarf galaxy, represent the final unstable phase before collapse. They are the brightest indicators of how far stellar birth in this environment has advanced. Each began life as a giant star burning hydrogen at extraordinary rates, and within a few million years nuclear fusion in their cores exhausted the lighter elements, forcing the stars to shed their outer layers through immense stellar winds. What remains is a blazing stripped core with temperatures exceeding tens of thousands of degrees Celsius, radiating ultraviolet energy and ejecting matter at supersonic speed. The winds from these stars shape the interstellar medium, creating expanding shells and cavities that fill the visible face of the galaxy. The existence of so many such stars within a small system like IC10 is a signature of exceptional activity, for Wolf-Rayet stars are rare even in larger galaxies. Their significance extends beyond their brilliance. They serve as natural laboratories for studying how metallicity affects the life cycles of massive stars. In high metallicity environments, heavy elements increase opacity and drive stronger winds, causing stars to lose mass faster and end their lives as lighter remnants. In IC10, with its low metallicity, winds are weaker, allowing stars to remain heavier until death. This creates a pathway toward the formation of unusually massive black holes. The Wolf-Rayet population here thus provides insight into the early universe, when conditions were similar and the first generations of stars could end in comparably heavy remnants. Through them, scientists glimpse the mechanisms that once produced the seeds of the supermassive black holes found in the centers of galaxies today. Astronomers classify Wolf-Rayet stars into two principal types, nitrogen-rich and carbon-rich, depending on the elements revealed in their spectra. The balance between these types varies from galaxy to galaxy, reflecting differences in age composition and stellar evolution pathways. In this dwarf starburst, nitrogen-rich stars dominate. Their presence suggests that the transition from hydrogen to helium burning occurs under conditions that slow mass loss, keeping the outer layers intact for longer. This pattern fits the broader evidence that low metallicity delays certain evolutionary stages and alters the structure of stellar winds. The data gathered from IC10 therefore contribute to refining models of how massive stars evolve under primitive chemical conditions. Spectroscopic surveys of the galaxy's Wolf-Rayet stars reveal powerful outflows reaching thousands of kilometers per second, carrying away mass at rates of 1/1,000,000th of a solar mass each year. These winds collide with surrounding gas, producing shock fronts that heat the material to millions of degrees. The resulting emission appears in X-rays, giving astronomers a way to map interactions invisible in optical light. Each star thus becomes both a source of light and a sculptor of its environment. The overlapping winds from many such stars form superbubbles, vast cavities tens or hundreds of light-years across filled with hot plasma. These structures, observed in radio and X-ray bands, testify to the combined force of stellar feedback within the galaxy's compact volume. Yet even as these winds disperse gas, they also trigger new creation. When shock fronts meet denser clouds, they compress them, leading to the next wave of star formation. This process ensures that the starburst sustains itself as one generation sets the stage for the next. Observations show dense clumps of gas at the edges of ionized bubbles, where cooling material is beginning to condense again. In this way, destruction and creation proceed together. The Wolf-Rayet stars act as both catalysts and terminators of star formation, dictating the tempo of evolution throughout the galaxy. Their lifespans are short, lasting only a few 100,000 years, but their deaths are momentous. When nuclear fuel is exhausted, the core collapses, producing either a neutron star or a black hole. The exact outcome depends on the star's final mass and rotation rate. In a low metallicity system like IC10, these conditions favor black hole formation. Several of the galaxy's X-ray sources are already identified as compact remnants, accreting matter from surviving companions. Each such binary system offers clues about how stellar mass metallicity and orbital evolution combine to create black holes. Among them, one stands out for its remarkable properties, the object later named IC10X-1, an eclipsing X-ray binary that became the focus of intense investigation. But before turning to that discovery, astronomers first sought to understand the broader environment from which it arose. The concentration of Wolf-Rayet stars in this galaxy is among the highest known in the local group. Their combined output of radiation and kinetic energy is staggering, easily exceeding that of all lower mass stars combined. These stars flood their surroundings with ultraviolet light, capable of ionizing vast regions of hydrogen gas. Their winds inject momentum and chemical elements into the interstellar medium, while their eventual explosions in supernovae seed the galaxy with heavier elements still. The balance between the destructive energy they release and the material they return defines the ongoing evolution of the system. Too much energy and the remaining gas could be expelled, entirely quenching future formation. Too little, and the gas remains stagnant, cooling without further collapse. The current conditions suggest a precarious equilibrium, one that allows sustained activity without total exhaustion. Observations in multiple wavelengths reveal the full impact of this population. Optical images capture the glowing shells of ionized gas surrounding clusters. Infrared maps show dust heated to hundreds of degrees as it absorbs ultraviolet radiation. Radio data trace the turbulent motions of gas inside expanding bubbles. X-ray surveys highlight regions where shock-heated plasma reaches millions of degrees. The total energy radiated by these processes when integrated across the galaxy rivals that of star-forming regions in galaxies an order of magnitude larger. It is through these combined energies that IC10 shines so brightly despite its small size. The chemical footprints left by Wolf-Rayet stars mark the ongoing transformation of the galaxy. Spectra of nearby gas clouds show elevated levels of helium and nitrogen, direct evidence of enrichment from stellar winds. The gradual build-up of these elements will shape future generations of stars, altering their structure and eventual fate. In this way, each wave of massive stars modifies the conditions for the next. Over cosmic time, these cycles of formation, enrichment, and collapse create the diversity of stellar populations that characterize mature galaxies. IC10 in its present state captures this process in miniature, a concentrated snapshot of galactic evolution, compressed into a dwarf system. The presence of so many massive stars also influences the galaxy's large-scale dynamics. Their collective winds drive outflows that escape the gravitational potential of the dwarf, carrying gas and dust into intergalactic space. These outflows may eventually feed neighboring systems or contribute to the diffuse medium that surrounds the local group. At the same time, the turbulence they create ensures that gas within the galaxy remains mixed, preventing localized depletion of elements. Through these opposing motions, loss outward and circulation within the system maintains a balance that sustains its luminous vitality. Seen across millions of light-years, IC10 appears small and dim, yet inside it is a furnace of creation and destruction. The Wolf-Rayet stars act as both the architects and the destroyers of its current form, sculpting the interstellar medium into bubbles and filaments, enriching it with heavy elements, and preparing it for the emergence of compact remnants. Their presence signals a moment of exceptional intensity in the galaxy's history, a brief but transformative episode that will define its chemical and structural identity for eons to come. Among these stars, hidden behind clouds of gas and dust, one system would soon reveal itself as an X-ray beacon, unlike any other offering direct evidence of a black hole locked in orbit with one of these dying giants. Amid the restless energy of the dwarf galaxy's luminous core, one point of high-energy light drew particular attention. It was first seen not as an image but as a rhythmic pulse of X-rays, a pattern that brightened and dimmed in measured intervals. This flicker stood apart from the diffuse glow of surrounding clusters or the steady emission of supernova remnants. Early catalogues recorded it under the name IC10X as X-1, an unremarkable label for what would soon become one of the most studied binaries in the local group. Its light curve displayed deep recurring eclipses, evidence that two objects circled one another in close orbit, one luminous and massive, the other small, compact, and almost invisible. From those repeating shadows, astronomers began to piece together the story of a system hidden within the haze of a distant galaxy. High-energy binaries are rare but powerful. They arise when a massive star transfers material to a collapsed companion, either a neutron star or a black hole. The infalling gas forms an accretion disk heated to millions of degrees, radiating strongly in X-rays. Each orbit causes fluctuations in brightness, as the disk tilts or becomes obscured by intervening matter. In this case, the donor star was soon recognized as a Wolf-Rayet star, one of the stripped wind-driven giants common in the galaxy's crowded center. Its surface expelled gas at several thousand kilometers per second, feeding the compact object through gravitational capture rather than through a steady stream. The geometry of the system produced complete eclipses roughly every day, and a rare configuration that allowed precise measurement of the orbit's scale and inclination. The first detailed analyses portrayed the unseen companion as extraordinary. Spectroscopic studies of the Wolf-Rayet star's motion, inferred from shifts in its helium and nitrogen lines, suggested that the compact object could exceed 20 times the Sun's mass, possibly the most massive stellar black hole yet identified. If confirmed, it would demonstrate that low metallicity environments like this one permit the formation of far heavier remnants than typically found in the Milky Way. Such a discovery would bridge the gap between ordinary stellar remnants and the massive black holes later detected through gravitational wave events. The small galaxy seemed to host an echo of those ancient conditions. As observations improved, a more cautious picture emerged. The broad emission lines of the Wolf-Rayet wind did not trace the star's centre of mass precisely. They originated in the moving layers of gas surrounding it. This motion distorted velocity measurements and exaggerated the derived mass. After correcting for these effects, estimates for the compact object's weight decreased, though it still fell comfortably within the black hole range. The revision did not diminish the system's importance, it refined it. The binary remained one of the clearest cases of a black hole, accreting from a Wolf-Rayet star, an arrangement exceedingly rare in the nearby universe. Different telescopes contributed pieces of the puzzle. The Chandra X-ray Observatory provided sharp imaging isolating the source from surrounding noise, while XMM Newton captured subtle spectral changes across each orbit. The brightness dropped abruptly during eclipses, confirming that the donor star's opaque wind could obscure nearly the entire disk. Between eclipses, fluctuations in hardness and intensity revealed the influence of clumped gas, showing that the accretion process was far from steady. The light that reached Earth carried the signature of turbulent flow magnetic heating and the scattering of photons through an uneven wind. Each variation was a coded message about the conditions near the event horizon. From these data, astronomers reconstructed the binary's dynamics. The Wolf-Rayet star orbits the compact object at a distance of only a few dozen solar radii, completing a full cycle in roughly 35 hours. Material stripped from its wind forms a transient disk that flares with X-rays as it spirals inward. The intensity of this radiation, together with its spectral shape, supports the conclusion that the accretor is a black hole rather than a neutron star. Its gravitational field is strong enough to heat infalling gas to extreme temperatures, producing a continuous stream of hard X-ray photons. During eclipses, the light fades almost completely before returning with mechanical precision, a heartbeat of gravity recorded across 2.5 million light-years. The discovery had implications beyond a single system. In galaxies rich in heavy elements, stellar winds remove too much mass for black holes of this size to form. But in the metal-poor environment of this dwarf galaxy, stars lose less material before collapse, leaving heavier cores. The binary thus offered direct evidence that low metallicity starbursts can produce black holes far more massive than those typical of the Milky Way. It became a cornerstone example, linking chemical composition to the cosmic population of compact objects. For researchers studying the origin of the heavy black holes that merge and radiate gravitational waves, this small flickering beacon provided a modern analogue of ancient processes that once shaped the early universe. The system also revealed the delicate relationship between stellar winds and orbital evolution. Each gust of gas alters momentum and drains angular energy, slowly tightening the orbit. Over time, this interaction will bring the two bodies closer together. When the Wolf-Rayet star finally exhausts its fuel, it too will collapse, likely forming another black hole. The resulting pair would drift in slow spiral until merging their final coalescence, releasing a burst of gravitational waves detectable across cosmic distances. Thus, the quiet modulation of X-rays in the present hints at a future event of immense scale, a story unfolding over millions of years. Technically, detecting such behavior at this distance was a triumph. X-ray photons are few, their paths easily scattered by interstellar dust and background noise. Observatories orbiting Earth collected them one by one, building a light curve through weeks of continuous observation. Each data point represented matter falling toward a boundary from which no signal can return. The precision of the resulting record, with its clean eclipses and repeating cycles, remains among the finest measurements ever obtained for an extragalactic binary of this type. For the wider astronomical community, what makes this system compelling is not only its mass or geometry, but its context. It resides within a galaxy that mirrors the physical conditions of the early cosmos, a place where metals are scarce and stars evolve differently. Observing such a binary provides a window into the processes that once shaped the first generations of black holes. In that sense, X-1 is both a present-day phenomenon and a historical analogue linking the nearby universe to its primordial origins. The faint pulse of its X-ray light carries the same story told by quasars and distant mergers, one of matter, spiralling into darkness, releasing energy as it vanishes beyond sight. Even after years of study, questions persist. The exact spin of the black hole remains uncertain, as does the fine structure of the accretion flow. Models continue to evolve, incorporating new data from space-based observatories and ground-based spectroscopy. Future missions capable of measuring polarization and finer spectral detail may reveal the orientation of the magnetic fields that govern the inflow. For now, the system remains both clear and mysterious, a measured heartbeat within a turbulent galaxy, small enough to appear as a single point yet vast enough to summarize the life and death of stars. The orbiting pair at the heart of the X-ray source represents more than a momentary interaction between a star and a black hole. It is a blueprint for an entire class of binary evolution that may echo across cosmic time. In the small low metallicity environment of this dwarf starburst, the formation of such a system becomes not only possible but likely. The same scarcity of heavy elements that allows massive stars to remain intact until collapse also ensures that their winds, though powerful, do not erode them beyond the threshold for black hole birth. The Wolf-Rayet star that now circles its invisible partner is itself a survivor of extreme internal pressure, its core already stripped of hydrogen and burning helium at extraordinary temperatures. Around it, the gravitational field of the compact object bends both space and time, drawing in streams of gas that spiral through invisible loops before vanishing into darkness. Between the two lies a region of continuous exchange, a tenuous bridge of radiation and wind where matter is both lost and reclaimed. Every orbit is a dynamic event. The compact object passes behind, and then before its luminous companion, moving through dense layers of stellar wind that vary in density from moment to moment. When the compact body emerges from eclipse, the X-ray emission rises sharply, peaking as the flow of accreting material stabilizes. As the orbit continues, that light softens and dims, modulated by the scattering of photons in the thick wind. The result is a smooth but irregular rhythm, each pulse carrying information about the density, speed, and composition of the gas. From Earth, 2.5 million light-years away, the signal arrives as a faint fluctuation in a steady stream of counts recorded by orbiting detectors. It is enough to trace the heartbeat of an object whose gravity prevents even light from escaping. In the region surrounding the binary, the effects of this invisible engine are unmistakable. The Wolf-Rayet star's wind collides with the high-energy outflow from the accretion disk, forming shock boundaries that glow faintly in X-rays and radio waves. These shocks create bubbles of hot gas that expand outward through the interstellar medium, merging eventually with larger cavities blown by other massive stars. The combined energy of these outflows sustains a network of turbulent fronts throughout the galaxy's central zone. Within those fronts, dense knots of gas are compressed to the point of collapse, seeding new clusters. The binary system thus participates in the same feedback loop as the broader starburst, the death throes of one generation setting in motion the birth of the next. The accretion process itself remains a subject of close scrutiny. In most binaries, matter forms a flattened disk as it spirals inward, radiating heat through friction and magnetic turbulence. Here, because the gas is supplied by a fast irregular wind, the flow is less orderly. Streams of material twist around the compact object, colliding and merging into a temporary disk that changes in shape with each orbit. The resulting X-ray emission fluctuates in both intensity and spectral hardness. Harder photons dominate when the accretion rate is high, indicating hotter, denser material near the event horizon. Softer emission prevails when the inflow thins or cools. The steady alternation between these states provides astronomers with indirect evidence of the conditions in a region too small and too distant to resolve directly. Measurements of the system's spectrum show features typical of black hole binaries, a thermal component from the inner disk, and a power law tail produced by inverse Comptons scattering in a corona of energetic electrons. These patterns, combined with the absence of pulsations characteristic of neutron stars, strengthen the case that the accretor is indeed a black hole. Yet the details remain uncertain. The system's geometry, the density of the stellar wind, and the inclination of the orbit all influence how radiation escapes. Models attempt to reproduce the observed light curve by varying these parameters, but none yet capture its full complexity. Even so, the agreement between observation and theory grows closer each year, and the binary remains a benchmark for understanding how massive black holes feed. Beyond the immediate system, the presence of such a luminous X-ray source influences its surroundings in measurable ways. High-energy photons ionize nearby gas, altering its temperature and chemical balance. Regions close to the binary become overpressured, driving small-scale flows that shape the nebular environment. Observations in optical emission lines show subtle enhancements in helium and nitrogen abundances, consistent with localized enrichment from the Wolf-Rayet wind. The gas closest to the system forms a halo of diffuse ionization that flickers in sync with the X-ray flux responding to its periodic eclipses. This delicate feedback, invisible to the naked eye, connects the microscopic processes of accretion to the macroscopic evolution of the galaxy's gas. From a broader perspective, this single binary acts as a bridge between the extremes of stellar and galactic evolution. It demonstrates how massive stars in low metallicity environments can evolve into black holes heavy enough to merge in detectable gravitational wave events. The physical conditions here, fast winds, compact orbits, and rapid evolution, mirror those inferred for the progenitors of the mergers, observed by modern detectors. In this way, the system provides a living link between local observation and cosmic history. Its flicker across the X-ray sky becomes a small but steady echo of the violent collisions that once shaped the early universe. The story of its discovery also reflects the evolution of astronomy itself. Instruments capable of detecting X-rays from millions of light-years away did not exist until the late 20th century. The identification of an eclipsing binary in another galaxy marked a milestone in sensitivity and precision. Each photon registered by the detectors carried an energy thousands of times greater than visible light, yet their arrival rate was so low that months of accumulation were required to construct a complete orbital curve. The resulting data combined technology and patience in equal measure, transforming a faint point in the sky into a system whose mechanics could be mapped and modelled. Even with these advances, mysteries remain. The spin of the black hole is unknown, the inclination of the orbit debated, and the future of the system uncertain. The Wolf-Rayet star will not live long. Within a few 100,000 years, it will collapse in a supernova, leaving behind a second compact remnant. Whether the explosion disrupts the binary or binds the two objects more tightly depends on asymmetries that cannot yet be predicted. If the pair survives, it will drift for millions of years before merging in a flash of gravitational radiation. If it does not, each remnant will wander separately through the galaxy, silent markers of a vanished partnership. Either outcome fits naturally within the cycles of creation and decay that define this small starburst world. To watch such a system is to witness the universe working at two tempos at once, the fast pulse of matter falling inward every second, and the slow unfolding of stellar evolution over millions of years. The periodic eclipses we record today are but brief moments in a story that began long before humanity existed and will continue long after. Through them, astronomers read the signatures of gravity's most extreme expression, a dance between light and darkness shaped by forces that remain beyond direct reach. In the dim heart of a distant dwarf galaxy, a black hole feeds, a star fades, and time itself seems to circle endlessly around their invisible bond. The orbital dance within this distant binary unfolds against a backdrop of restless energy. Around the pair, stellar winds, supernova remnants, and diffuse radiation fill the galaxy's inner regions with motion. The light from clusters of young stars scatters through layers of gas and dust, while magnetic fields weave invisible currents that guide charged particles across vast distances. This turbulence creates an environment in which gravity, radiation, and motion are locked in continual negotiation. Within it, the compact system that hosts the black hole becomes both a product and a participant of the wider cosmic ecosystem, shaping its surroundings as much as it is shaped by them. The X-rays it emits pierce the galaxy's internal haze, faintly illuminating gas that otherwise would remain dark each photon, a record of matter transformed by gravity into light. Over time, subtle variations in the binary's emission reveal the complex structure of the accreting gas. The X-ray spectrum softens and hardens in repeating cycles, showing that the flow of material is neither smooth nor constant. Clumps in the Wolf-Rayet star's wind create irregular bursts of brightness, like weather patterns in a planetary atmosphere. These episodes demonstrate how chaotic a wind-fed accretion process can be in contrast to the steady inflow seen in systems where matter passes through a stable disk. The wind around the donor star is dense, accelerated by radiation pressure, and threaded with magnetic irregularities. As fragments of this wind fall inward, they spiral through shock fronts and turbulence, releasing brief flashes of high-energy radiation before vanishing across the invisible boundary of the black hole's event horizon. This constant flicker carries the imprint of countless small impacts, collisions of gas and gravity playing out on a microscopic scale. Closer to the compact object, the physics grows more extreme. The accretion flow becomes hotter, thinner, and faster, transforming into a disk only a few tens of kilometers thick yet extending thousands of kilometers wide. Friction and magnetic shear convert orbital energy into heat, producing temperatures high enough to ionize atoms completely. In this region, photons scatter repeatedly from energetic electrons, forming the power law component of the observed spectrum. Beyond the disk, a tenuous corona of plasma radiates in hard X-rays, its structure fluctuating with the flow beneath. Some of the emitted photons strike the inner edge of the disk and are reflected, creating subtle, spectral signatures known as ion emission lines. These reflections allow scientists to probe the geometry of the region, where space begins to twist under the black hole's gravity. The precise shape and energy of those lines hint at how fast the black hole spins, though the data remain too limited to give a definitive value. Outside the immediate binary, the influence of this small engine spreads through the surrounding gas. High-energy photons escape the system and strike nearby molecular clouds, heating their surfaces and altering their chemistry. Observations of emission lines from ionized oxygen and neon reveal localized regions of excitation centered near the X-ray source. Such pockets of energized gas act as markers of feedback, the process by which compact objects return energy to their environment. Though the total power released is small compared with the combined luminosity of the galaxy's many stars, it is focused and efficient, capable of changing the temperature and ionization of gas over significant distances. In this way, the black hole becomes part of the same network of cause and effect that links every scale of galactic evolution from individual stars to the interstellar medium. The dynamics of the orbit itself continue to draw study, because the system's period can be measured with high precision. Even slight changes offer insight into the forces at work. A gradual drift in the timing of eclipses could signal mass loss from the Wolf-Rayet star or angular momentum exchange through the wind. If the orbit shrinks, gravitational radiation might already be extracting energy from the system, though at a rate far too small to detect directly. Over millions of years, such losses accumulate, bringing the two bodies inexorably closer. Models suggest that within a few 100,000 years after the donor star's collapse, the remnants will form a double black hole binary. This configuration will emit gravitational waves as it spirals inward, culminating in a merger that releases more energy in a fraction of a second than all the stars of the observable universe combined during that moment. While that distant future remains far beyond observation, the current phase offers a unique opportunity to study the stages leading toward it. The combination of low metallicity, strong winds, and close orbits in this small galaxy represents the precise set of conditions thought to give rise to the heavy black hole pairs detected by modern gravitational wave observatories. The binary's behavior therefore bridges two realms of astrophysics, the X-ray emission of feeding black holes, and the gravitational waves of merging ones. What is seen here in light foreshadows what might one day be detected in the silent language of space-time. The presence of this energetic pair also serves as a reminder of the galaxy's larger cycle of creation. Massive stars live briefly but leave profound traces. Their winds enrich the interstellar medium, their explosions stir and heat the gas, and their remnants continue to influence the environment long after their deaths. Around the binary, the same processes are repeated on smaller scales, the outflow from the Wolf-Rayet star interacting with the inflow toward its companion. Energy moves in two directions at once, outward through radiation and inward through accretion, balancing destruction and renewal. In the delicate equilibrium between these motions lies the key to the galaxy's vitality. From a technical perspective, studying such a distant and compact system demands collaboration across many observatories. Optical telescopes track the visible star's spectrum, measuring its motion and wind properties. Infrared instruments penetrate the dust that obscures the galaxy, refining the brightness and temperature of the donor. X-ray satellites monitor the high-energy emission with time resolution fine enough to follow every orbit. Each wavelength contributes a different layer of understanding, and only by combining them can the full picture be assembled. The result is a composite portrait of two bodies locked in motion, their mutual gravity shaping the light that escapes across millions of light years. In the broader context of astrophysics, this binary stands as a natural link between the life cycles of stars and the evolution of galaxies. It illustrates how individual stellar remnants can return energy to their surroundings, influence star formation, and perhaps even escape into intergalactic space after violent events. The processes observed here on a miniature-scale mirror those that govern active galactic nuclei, where supermassive black holes feed in similar fashion but on vastly larger scales. In this sense, the tiny system functions as a scaled-down model of cosmic accretion, governed by the same equations and forces that rule the hearts of galaxies. For now, the faint flicker of its X-rays continues, uninterrupted a steady pulse in the background of the local group. Each orbit marks another transfer of matter, another transformation of gravitational potential into radiation. From Earth's perspective, the light is constant and remote, yet it encodes the full story of motion, interaction, and change. Within a galaxy no larger than a small spiral arm, a black hole and a dying star enact a process that has occurred countless times across the cosmos. In their orbit we find the same pattern, repeated everywhere, matter drawn inward, energy cast outward, and the universe continuing its endless exchange between light and gravity. The steady rhythm of radiation from the compact binary forms only one part of the larger pattern of energy within its host galaxy. Surrounding the luminous pair are fields of hot plasma shells of expanding gas and filaments that stretch outward from the central starburst. Together they create a web of activity that sustains the galaxy's brightness and defines its character. At its scale, gravity and radiation act in concert, shaping an environment where nothing remains still for long. In this restless equilibrium, the black hole system functions as a localized source of feedback, a point of concentrated power influencing gas flows across distances far greater than its orbit. Over thousands of years, the cumulative effect of its emission and outflows contributes to the evolution of the galaxy's central region, though on timescales too vast for direct observation. The gas surrounding the binary is not uniform. Observations across multiple wavelengths show that it consists of layered structures, each responding differently to radiation and pressure. Closest to the stars lies an envelope of highly ionized material heated to millions of degrees. Farther out, a region of partially ionized gas glows in emission lines of hydrogen and oxygen, creating the visible nebulae seen through narrow filters. Beyond that extends a diffuse halo of cooler hydrogen and dust, gradually blending into the galaxy's broader interstellar medium. Within these layers, the physical conditions change continuously. Density drops, temperature falls, and radiation weakens with distance. Yet all remain linked through the interplay of light and matter originating from a few compact sources. Astronomers studying this region combine data from optical infrared and radio surveys to build three-dimensional models of its structure. These models reveal cavities where strong winds have swept material aside and dense clumps where shock waves have compressed it. The brightest emission comes from the interfaces between these regions, where energy exchange is most intense. In those border zones, ionized gas cools and recombines, releasing photons that carry signatures of the local temperature and composition. By measuring these signatures, scientists reconstruct the physical history of the gas, how long it has been exposed to radiation, how fast it moves, and whether it is being expelled from the galaxy or falling back toward its core. In this way, the story of the X-ray binary becomes inseparable from that of the surrounding interstellar landscape. The influence of high-energy sources such as this one extends well beyond their immediate surroundings. When their radiation interacts with dust grains, it alters the balance of heating and cooling that determines where new stars can form. Dust particles absorb ultraviolet and X-ray photons, raising their temperature and re-radiating the energy in the infrared. This process creates localized warm zones visible in long wavelength maps. Over time, the repeated heating and compression of gas by stellar winds and radiation can either trigger or suppress further star formation depending on the prevailing conditions. In some regions of the Dwarf galaxy, evidence suggests that starbirth has been quenched near the most active clusters, while in others new clouds are collapsing just beyond the reach of the strongest radiation. Such spatial patterns indicate that feedback is not uniform but self-regulating, ensuring that the galaxy neither burns out its gas too quickly nor allows it to stagnate. At the same time, large-scale motions continue to shape the galaxy's structure. Neutral hydrogen maps reveal streams of gas extending far beyond the optical disk, possibly remnants of earlier outflows or interactions with neighboring systems. The energy released by supernovae and compact binaries helps drive these flows, pushing material into the surrounding halo. Some of the gas may escape entirely, enriching the intergalactic medium with metals produced in stellar interiors. Yet gravitational pull ensures that part of it will eventually fall back, raining onto the galaxy and replenishing the fuel for future star formation. This circulation of matter expulsion, cooling, and return forms a self-sustaining loop that defines the long-term evolution of galaxies both large and small. Within this broader cycle, the compact binary serves as a microcosm of cosmic processes. Its accretion disk converts gravitational energy into radiation, with remarkable efficiency, achieving luminosities millions of times greater than the Sun's, despite the small size of its central engine. The mechanics are the same as those operating in quasars and active galactic nuclei, differing only in scale. Matter falling into the black hole releases potential energy in the form of light and heat, transforming the surrounding medium. In this sense, the system offers a bridge between the extremes of astrophysics, a stellar mass black hole, behaving as a miniature version of the engines that power entire galaxies. Studying it helps clarify how energy flows from compact objects to their environments across the universe. As instruments become more sensitive, subtle variations in the binary's emission reveal new details. Minute delays between different energy bands hint at the geometry of the accretion flow, while the shape of emission lines indicates the velocity of material near the black hole. In some observations, astronomers detect faint quasi-periodic oscillations, tiny rhythmic changes in brightness that may correspond to vibrations in the disk or precession of its inner regions. These signals, though weak, provide rare glimpses of conditions just outside the event horizon. They represent one of the few ways to probe directly the behavior of matter under extreme gravity, where theory and observation meet at the boundary of the possible. Even the surrounding starlight plays a role in shaping what is seen. The combined glow of clusters within a few hundred light-years adds a soft background that complicates measurement, but also contextualizes it. Against that luminous backdrop, the binary's sharp X-ray emission appears as a single, bright point, a contrast of precision amid chaos. By correlating its variability with the patterns of star formation, nearby researchers trace the interplay between microscopic and macroscopic scales, the influence of one system on many. This relationship defines the essence of astrophysics, the understanding that every small object, no matter how compact or distant, contributes to the balance of the cosmos as a whole. As with much of modern astronomy, progress depends on cooperation between observatories and the accumulation of data over long spans of time. Space-based telescopes monitor the binary's X-ray output, while ground-based instruments track its optical counterpart and the surrounding nebula. Radio arrays map the diffuse emissions produced by charged particles accelerated in shocks. When combined, these datasets reveal not a static picture, but a living one constantly shifting. As stars evolve, winds collide and radiation ebbs and flows. The same cycles that govern this single galaxy operate everywhere: creation, from collapse energy, from gravity, light from darkness. Viewed from Earth, the entire system occupies only a fraction of a degree in the sky, hidden behind the Milky Way's thickest dust lanes. Yet its influence extends far beyond its size, reminding observers that even the smallest galaxies can host processes of universal importance. Each photon that leaves the vicinity of the black hole carries within it a record of transformation of mass becoming energy, and energy dispersing into space. The faint flicker of that light after travelling millions of years through interstellar and intergalactic distance reaches our detectors as a whisper of the cosmic order matter, falling gas moving and time unfolding in the same relentless rhythm that governs all galaxies. The X-ray binary, though occupying a single point in space, anchors a chain of interconnected processes that ripple through the dwarf galaxy structure. Each phase of its evolution leaves a measurable imprint. Radiation alters gas chemistry, winds sculpt the surrounding medium, and the eventual collapse of its companion will inject a new shock of energy into the already turbulent core. In studying this one system, astronomers glimpse the mechanisms that define how small galaxies evolve under the influence of massive stars and their remnants. The interplay between feedback and gravity, between loss and replenishment, is written across every wavelength of observation. What begins as a localized interaction between a star and a black hole extends outward until it shapes the entire environment, linking microscopic forces to galactic dynamics. At the scale of the binary itself, the physics of accretion governs the flow of energy. The material captured from the Wolf-Rayet star's wind does not fall directly into the black hole, but forms a transient disk, its inner regions rotating at nearly a third the speed of light. Magnetic fields within this disk drive turbulence, redistributing angular momentum and allowing gas to spiral inward while releasing enormous quantities of heat. The emitted X-rays, fluctuating with every orbit, reveal the disk's temperature and density profile. The brightest phases coincide with periods of enhanced inflow, possibly triggered by irregularities in the stellar wind. As gas approaches the event horizon, it becomes so hot that individual atoms disintegrate into plasma. Some of this matter plunges inward, but a small fraction is expelled again in outflows powered by radiation pressure and magnetic fields, forming a feedback loop between inflow and escape. This constant exchange produces an observable pattern across multiple energy bands. The hardest X-rays trace the innermost regions near the black hole, while softer emission arises from the outer disk and scattered light in the stellar wind. By monitoring the timing and ratio between these components, scientists infer the geometry of the system, its tilt, its size, and the spatial distribution of hot and cooler regions. Variability on timescales of minutes suggests that dense clumps of gas occasionally obscure the central source before disintegrating under radiation pressure. These rapid changes offer a dynamic view of a process that otherwise remains invisible. Every fluctuation becomes a form of remote sensing, translating light into structure, variability into understanding. Beyond the immediate binary radiation from the accretion disk and the Wolf-Rayet star shapes the galaxy's internal climate. Ionization fronts expand outward from the system, heating nearby clouds and altering the equilibrium between atomic and molecular gas. Observations in narrowband optical filters show faint filaments of glowing hydrogen surrounding the central clusters, relics of the ionized zones produced by high-energy photons. Within these filaments, turbulence stirs the gas into knots that may later condense into new stars once the energy subsides. The pattern repeats endlessly. Each generation of massive stars creates the conditions for the next, through both destruction and renewal. IC10, though, small, exemplifies this balance between activity and rest, between chaos and structure. The binary's contribution to this process can be measured indirectly through its total energy output. When integrated over time, the X-ray luminosity represents a significant portion of the galaxy's entire radiative budget. Even though the absolute number is modest by extragalactic standards, the concentration of that energy in a single point makes it influential. High-energy photons penetrate deeply into surrounding gas, producing secondary ionizations and heating, that extend far beyond the visible source. In radio maps, the region around the binary glows faintly with synchrotron radiation from electrons accelerated in shocks, evidence that the energy released near the black hole propagates outward through multiple channels. Thus the system functions as a miniature active nucleus within its host, its energy output small in total, but immense in local effect. Over longer timescales, the evolution of the binary will alter the composition of the galaxy itself. As the Wolf-Rayet star continues to lose mass, its orbit will widen slightly, and its wind will inject more helium and nitrogen into the surrounding medium. When it eventually collapses, the supernova explosion will momentarily rival the combined light of the entire galaxy. The resulting remnant, whether a second black hole or a neutron star, will either disrupt the orbit or bind more tightly to the existing one. If the two remnants remain gravitationally coupled, they will slowly lose energy through gravitational radiation spiraling together until merging in a burst of waves that will ripple through space-time. Though that final event lies far in the future, the binary's present state already contains the seeds of its destiny. Observing it today is akin to reading the prologue of a story whose conclusion will unfold long after human observers have vanished. Understanding such systems has required decades of refinement in both technology and theory. High-resolution spectroscopy, precision timing, and numerical modelling now combine to interpret phenomena that were once beyond measurement. Simulations of wind-fed accretion reproduce many of the observed features from variable luminosity to the characteristic shape of eclipse light curves. These models suggest that much of the complexity arises from the interaction between the Wolf-Rayet wind and the compact object's gravity. The wind is not smooth but fragmented, filled with dense clumps that intermittently feed the accretion flow. When these clumps collide or fragment near the black hole, they produce brief surges in brightness. Such insights would be impossible without the sustained accumulation of data demonstrating how the patient observation of a single system can illuminate universal principles. The environment in which this occurs remains as important as the process itself. The low metallicity gas of the dwarf galaxy modifies every aspect of stellar and binary evolution. With fewer heavy elements to drive mass loss, the stars remain more massive and compact, and the black holes they produce retain a larger fraction of their progenitors' mass. This difference explains why the binaries formed in such galaxies are likely to host heavier black holes than those found in metal-rich environments like the Milky Way. The lessons drawn from this nearby system thus extend to the distant universe, where early galaxies shared similar chemical simplicity. By observing IC-10, astronomers effectively look backward in time, studying in detail what could once only be inferred from theory. Even with growing knowledge, mysteries persist. The spin of the black hole remains uncertain, the structure of the accretion disk ambiguous, and the role of magnetic fields difficult to measure. Instruments of the next generation, sensitive to both polarization and faint X-ray echoes, may one day reveal how matter flows and radiates within a few gravitational radii of the event horizon. For now, each new observation refines the limits of understanding. The binary remains a benchmark, both ordinary and exceptional, a stellar remnant obeying the same laws as countless others, yet positioned in a setting that magnifies its significance. Seen from Earth, it appears as a single flickering point buried in dust near the edge of a minor galaxy. Yet within that faint light lies the full cycle of stellar life and death compressed into the space of a few million kilometers. Matter falls inward, radiation flows outward, and time stretches in both directions toward the ancient conditions that shaped the first black holes and toward the future merger that will end this one. The system stands as a quiet emblem of cosmic continuity, linking the processes of galaxies large and small, near and remote through the shared language of gravity, heat and light. In the wider perspective of cosmic evolution, the binary now orbiting in the heart of this dwarf starburst is more than an isolated curiosity. It represents one of many pathways through which galaxies enrich and transform themselves. The interplay between radiation, gravity and matter that defines its existence is the same mechanism that has governed the universe since the first stars ignited. Every photon escaping from its accretion disk carries away a trace of gravitational energy, and every atom falling inward becomes part of the cycle that links microscopic motion to cosmic structure. In this quiet corner of the local group, the story of black holes and galaxies is written in miniature, showing how the same rules apply across scales differing by billions in size and energy. At the most immediate level, the system acts as a small but steady source of power for its surroundings. The X-rays it emits pass through the local medium ionizing atoms and heating the gas, while ultraviolet radiation from its companion continues to drive chemical reactions that create and destroy molecules. The result is a dynamic equilibrium, an environment constantly shifting between order and chaos. For nearby molecular clouds, such exposure can be both destructive and creative. Too much radiation dissociates the bonds that hold molecules together, yet a measured dose can free elements that seed new reactions. In this way, the energy of the binary subtly regulates the state of the interstellar medium, influencing where and when new stars might form. The effects of this regulation are visible in the distribution of ionized regions around the galaxy's central clusters. High-resolution images show cavities and shells whose edges glow faintly in hydrogen emission, tracing the boundaries between hot plasma and cooler gas. These structures expand over time as radiation pressure and stellar winds push outward. The X-ray binary contributes to this expansion, adding its concentrated energy to that of the larger population of massive stars. The resulting pattern resembles ripples from overlapping stones cast into water, spherical waves of ionization, intersecting, merging and fading into one another. Through these overlapping motions, the central region of the galaxy remains a zone of constant renewal, where compression and rarefaction act in balance. Such processes echo those found in much larger systems. In massive galaxies, feedback from central black holes regulates star formation by heating and expelling gas. In this small galaxy, the same physics unfolds on a reduced scale. The comparison illustrates the universality of accretion-driven feedback. Whether the central object weighs a few dozen solar masses or billions, its interaction with surrounding matter follows the same fundamental laws. This parallel makes IC-10 and its X-ray binary a bridge between stellar and galactic astrophysics, a nearby demonstration of the principles that govern structures far beyond human reach. The low metallicity of the environment adds another layer of significance. Because heavier elements are sparse, the gas cools less efficiently, making star formation more burst-like and concentrated. When such bursts occur, they produce a higher fraction of massive stars than in metal-rich galaxies. The subsequent evolution of these giants favours the creation of heavy black holes and compact binaries like the one observed here. The system thus represents not an anomaly, but a predictable outcome of its chemical setting. In studying it, scientists refine their understanding of how initial conditions determine the population of stellar remnants across the cosmos. The lessons learned reach far beyond the boundaries of the local group, extending to the epoch of rionization, when the first galaxies illuminated the early universe. Observationally, the binary remains a challenge. Its faint optical counterpart is nearly lost in the crowd of bright clusters, and foreground extinction from the Milky Way absorbs much of its light. Only through a combination of infrared and X-ray data can astronomers trace its behavior. Repeated monitoring reveals gradual changes in brightness between eclipses, possibly linked to fluctuations in the donor star's wind or to variations in the accretion rate. Each dataset adds a fragment to a puzzle that spans decades of observation. The long-term stability of the system's orbital period suggests that despite the violence of its environment, it has reached a form of equilibrium, a steady dance between attraction and release that may persist for hundreds of thousands of years before the next transformation. The data collected from this single object have also informed studies of similar binaries in other galaxies. Comparisons show that systems in low metallicity environments tend to produce higher X-ray luminosities and longer-lived accretion phases. These properties arise naturally from the slower mass loss of their massive stars and the denser winds that accompany them. In this way, the binary in the dwarf galaxy serves as a reference point, allowing astronomers to calibrate models that explain the distribution of X-ray sources throughout the universe. Each new discovery of a similar system strengthens the link between local observation and cosmic context, showing how individual stars contribute to the overall energy balance of galaxies. The radiation from such systems also influences the visibility of their hosts at great distances. In deep surveys, the cumulative emission from populations of X-ray binaries provides a measurable fraction of the total X-ray background that permeates the sky. These photons, traveling across billions of light-years, carry the integrated imprint of countless small galaxies undergoing similar starburst phases. The study of nearby examples like IC10 enables scientists to interpret that diffuse background as a record of cosmic history, tracing the build-up of heavy elements and the rise of the first black holes. Thus, the faint light from one system becomes a key to understanding the glow of the universe itself. From a theoretical standpoint, the system challenges existing models of binary evolution. The coexistence of a compact object and a Wolf-Rayet star in such close orbit raises questions about how the pair avoided premature merger during earlier stages. Simulations suggest that mass transfer and stellar winds must have been finely balanced, with each phase of evolution adjusting the separation to maintain stability. The persistence of this delicate configuration shows how diverse the outcomes of stellar interaction can be. Even small variations in mass rotation or chemical composition could have produced an entirely different result, perhaps a single massive black hole or a disrupted remnant scattered into intergalactic space. That the binary survives at all underscores the precision of cosmic mechanics operating under seemingly chaotic conditions. Future instruments will deepen the study of this remarkable pair. Next-generation X-ray observatories will measure the polarization of emitted light, revealing the orientation of magnetic fields within the accretion disk. Infrared interferometers will resolve the wind of the Wolf-Rayet star, mapping its density and velocity structure in unprecedented detail. Radio telescopes will continue to search for traces of jet-like outflows, which if detected would connect the system even more closely to the physics of quasars. Each advance will refine the picture of how matter behaves in the presence of intense gravity and radiation, linking observation to fundamental physics. To an observer standing on Earth, the galaxy hosting this system remains a faint smear of light, almost invisible to the unaided eye. Yet within that small patch of sky, forces of unimaginable scale are at work. The black hole continues to feed. The star continues to shed its layers. Gas clouds drift, collapse, and reform. In the midst of it all, the same laws that govern the largest structures in the universe act upon the smallest, ensuring continuity between the immense and the minute. The quiet pulse of X-rays from this distant source becomes a metronome of cosmic balance, marking the passage of energy from matter to light, from the finite to the infinite. As time passes on astronomical scales, the black hole and its companion continue their steady exchange, enclosed within an environment of complex motion and luminous unrest. Around them, the dwarf galaxy maintains its restless state. Gas flows collide, stars are born and destroyed, and light escapes through narrow lanes of transparency carved by wind and radiation. The binary, though tiny in proportion to its surroundings, remains one of the dominant points of power within this system. Each orbit repeats the same choreography, matter drawn from a stellar wind converted to heat and light, and then dispersed again into the surrounding medium. From this process emerges not only the characteristic flicker of X-rays, but also the quiet shaping of space itself, as radiation pressure and gravitational attraction weave a dynamic equilibrium. The scale of energy transformation occurring within the orbit is almost beyond measure. Every second, material weighing thousands of tons per second falls toward the black hole, losing gravitational potential energy that is converted directly into radiation. The efficiency of this conversion, often around 10%, is among the highest known in the universe, rivaled only by the processes occurring near supermassive black holes in distant quasars. In essence, the system operates as a miniature engine of cosmic transformation, a link between the life of a star and the deep physics of curved space-time. The photons produced in this act travel outward, crossing the dense stellar wind, scattering through the galaxy's gas, and eventually traversing millions of light-years before reaching human instruments. Each one is a messenger carrying the record of matter consumed by gravity. Even at such distances, careful observation reveals the subtle variability that defines the system. The X-ray light curve, when monitored over many years, shows both stability and evolution. Eclipses remain regular, indicating a consistent orbital period, but small shifts in their timing hint at gradual changes in mass or angular momentum. These deviations could arise from mass loss through stellar wind, from accretion onto the black hole, or from the influence of tidal forces acting between the two bodies. The orbit itself is a living record of the balance between competing effects: radiation driving matter away, gravity drawing it inward, and time altering both. With each passing epoch, these forces will reshape the binary until one final collapse resets the cycle entirely. Beyond the immediate pair, the galaxy continues to reflect their influence. X-rays ionize the surrounding gas, while the ultraviolet glow of the Wolf-Rayet star drives the formation of extended nebulae visible in optical emission lines. These bubbles and shells serve as time markers, expanding at known speeds and preserving the history of energy release. By mapping their size and velocity, astronomers can reconstruct the sequence of outflows that have occurred across thousands of years. Each shell represents a layer of memory, a fossilized imprint of earlier activity. Together they form a visible archive of the forces that connect a single binary to the evolution of its host galaxy. At greater distances from the core, the effects of radiation soften into the diffuse light of the galaxy's outer halo. Here, cooler hydrogen mingles with dust grains formed in past supernovae, and the constant bombardment of high-energy photons maintains a tenuous glow. In these outer regions, astronomers find hints of the galaxy's past interactions, trails of gas stretching outward like faint arms, perhaps remnants of encounters with smaller neighbours. These features suggest that the galaxy has not lived in isolation, but has exchanged material with its environment, drawing in fresh gas while expelling enriched matter into intergalactic space. The black hole system plays a small but measurable part in this broader exchange, adding its own fraction of energy to the collective flow. Within this environment, the Wolf-Rayet star approaches the end of its life. Its mass loss rate remains immense, yet the process cannot continue indefinitely. Once the fuel in its core is exhausted, the star will collapse, releasing an explosion that will briefly outshine the entire galaxy. The energy of such an event will sweep through the existing cavities, reheat the surrounding gas, and reset the conditions for future formation. If the supernova leaves behind another black hole, the two remnants may remain bound, continuing their gravitational waltz until they eventually merge. The light from that final collision will not come as photons, but as ripples in space-time, a gravitational signal crossing the universe long after the visible galaxy has faded. In that future event lies the ultimate consequence of everything observed today. Between now and that far-off moment, the binary continues to provide clues about the processes shaping the cosmos. Its behavior offers a natural test for theories of stellar evolution, accretion physics, and feedback in small galaxies. By comparing its properties to those of similar systems in other environments, scientists refine models of how metallicity, mass, and radiation interact to produce different outcomes. Each observation deepens understanding of how the universe builds complexity from simple ingredients. The study of this one system contributes to knowledge reaching from the smallest scales of plasma turbulence to the largest questions about galaxy formation. The surrounding galaxy, for its part, remains a dynamic stage. Star clusters continue to form and dissolve, releasing new generations of massive stars into the same feedback cycle that created the black hole system in the first place. Supernovae erupt, enriching the gas with heavier elements. Dust condenses and scatters, forming temporary shrouds that dim the starlight until radiation breaks them apart again. Across millions of years, the balance of energy gradually shifts. The initial burst of formation will fade, the gas will thin, and the bright irregular patches will cool into quieter star fields. In this slow transformation, the role of compact objects like the X-ray binary persists, acting as long-lived beacons of the galaxy's most energetic past. From Earth, the system's flicker appears constant, unaffected by the long timescales that govern its evolution. Telescopes collect photons that left the galaxy 2.5 million years ago, when early hominins still walked on African plains. In this way, the light reaching human eyes is already a message from deep time carrying information about an event still unfolding far away. To study it is to bridge epochs, connecting the evolution of distant stars with the unfolding history of life on our own planet. The galaxy becomes not only a physical object, but also a temporal mirror reflecting a universe always older than it appears. In the quiet of its observation, one realizes that the same forces shaping this remote system act everywhere. Gravity collapses, matter radiation resists it, and between them lies the delicate space where structure emerges. The binary embodies this balance perfectly: a star that fights to disperse its material, and a black hole that draws it inward, the two locked in perpetual opposition. Their interaction demonstrates the universe's fundamental symmetry creation, arising from destruction order born from chaos and energy, forever cycling between visible and unseen forms. Long after the final merger erases both the light and elements they release, will remain as part of the interstellar medium waiting to form something new. The story of IC-10 and its compact heart is in the end the story of all galaxies, a cycle of birth, transformation and renewal sustained across cosmic time, quiet and unending beneath the motion of stars. The long arc of time within the galaxy ensures that nothing remains unchanged. Even the apparent constancy of the X-ray binary hides a slow evolution, measured not in human years but in millennia. The orbit that now completes in just over a day and a half will, through mass loss and radiation, alter imperceptibly with each cycle. The Wolf-Rayet star grows lighter as it continues to shed its outer layers, while the black hole grows heavier as it feeds. The balance between these changes governs the future of the pair, dictating whether the system widens or contracts. The exchange is subtle but relentless, a dialogue carried by gravity and light. As the black hole's pull strengthens, the geometry of the orbit shifts, the timing of eclipses drifts, and the nature of the wind itself adjusts in response. This slow choreography, mass flowing outward and inward in equal measure, illustrates the precision of cosmic equilibrium maintained even in apparent chaos. The surrounding galaxy reflects this same principle. Its starburst phase, though brilliant, cannot last forever. The enormous output of radiation and wind from massive stars gradually depletes the reservoirs of cool gas from which new stars are born. The mechanical energy released by supernovae and by systems like the X-ray binary stirs the interstellar medium into turbulent motion, driving gas out of the densest regions. For a time, this activity sustains a balance, recycling material between phases of collapse and expansion. Eventually, however, the supply of unheated gas dwindles and the rate of formation declines. The galaxy will then enter a quieter epoch dominated by the aging remnants of earlier generations, white dwarfs, neutron stars, and black holes, orbiting silently in the remnants of the once bright clusters. In this sense, the current luminosity of the galaxy is only a brief flare in a long cosmic lifespan. While the future dims, the present remains instructive. Each component of the galaxy's structure can be read as a record of energy exchange. Filaments of hydrogen trace where stellar winds collide. Radio-bright loops outline bubbles of ionized gas driven by collective feedback. Even the diffuse X-ray glow observed between clusters represents the sum of countless small events: supernova shocks, wind collisions, and emission from binaries like the one dominating the center. When viewed together, these layers form a continuous spectrum of energy transformation from the small to the vast. The dwarf galaxy thus serves as a natural laboratory where processes that shape giant systems can be studied in concentrated form. Its scale makes it possible to observe directly the connections between individual stars and global dynamics that in larger galaxies remain concealed by distance. The binary's influence extends beyond light and heat. The material it releases atoms stripped from the Wolf-Rayet star and carried outward in wind adds to the enrichment of the surrounding gas. These elements, heavier than hydrogen and helium, are the building blocks of future planets and life. In this small galaxy, where metallicity remains low, each such contribution is significant. Over millions of years, repeated cycles of stellar evolution will gradually increase the abundance of these elements, changing the thermal and chemical behavior of the gas. The system therefore participates in the long-term evolution of the galaxy's composition, ensuring that each new generation of stars forms from material slightly richer than before. In this slow accretion of heavy elements lies the seed of complexity that defines the universe's progression from simplicity to diversity. Astronomers use detailed spectral measurements to quantify these changes. The ratios of emission lines in the surrounding nebula reveal both the density of the gas and its chemical composition. Variations in those ratios over time suggest that localized enrichment is already occurring. By comparing these observations to models of stellar evolution, researchers can estimate how much material the Wolf-Rayet star contributes to the interstellar medium each year. The results confirm that feedback from massive stars and binaries dominates the chemical growth of small galaxies, while less massive stars play supporting roles. This finding connects the fate of one binary to the evolution of entire galaxies across cosmic history. The eventual collapse of the donor star will mark the end of one phase and the beginning of another. When the star explodes as a supernova, it will expel much of its remaining mass into the surrounding region, briefly illuminating the galaxy in a flash, visible across millions of light years. The shock wave from that explosion will collide with existing shells of ionized gas, compressing them, and perhaps triggering new star formation along their fronts. Whether the compact binary survives, the explosion depends on the asymmetry of the blast. If the kick imparted to the newly formed remnant is small, the system may remain intact, evolving into a double black hole pair. If the kick is large, the remnants could separate, sending one hurtling into intergalactic space. In either case, the explosion will reshape the local environment, adding new layers to the mosaic of feedback that defines this galaxy's structure. On human timescales, these changes are imperceptible, yet the traces of earlier transformations are visible everywhere. The surrounding nebulae, with their complex geometry of filaments and arcs, record the cumulative history of such events. Each bubble of glowing gas began as a point of high pressure, expanding into surrounding material at speeds of hundreds of kilometers per second. As the shock fronts slowed, they cooled and began to recombine, leaving behind the intricate pattern seen today. The binary sits near the center of one such structure, a faint reminder of the many cycles that have preceded it. Studying these features allows astronomers to reconstruct the timing of past episodes, linking the history of the galaxy to the physics of its most energetic systems. The knowledge gained from this remote corner of the universe informs the understanding of phenomena far beyond it. The principles governing the interaction of radiation and matter here also apply to quasars at the hearts of distant galaxies, and to the bursts of energy that mark the deaths of the most massive stars. By examining a nearby example, scientists can test models that would otherwise remain abstract. Each observation of the binary, each spectrum of its host, becomes a step toward deciphering the universal language of feedback that governs the cosmos. As the galaxy's activity eventually subsides, the remnants it leaves behind will persist. The black hole, heavy and silent, will continue to orbit whatever companion remains until gravitational decay brings it to rest. Around it, stars will cool and fade their light, absorbed by drifting dust and re-emitted as a faint infrared glow. Over hundreds of millions of years, the once bright dwarf will dim into a cloud of old stars, still carrying within it the heavy elements forged in its brief era of brilliance. The echoes of its past supernova shells, enriched gas and compact remnants will testify to the forces that once shaped it. In this distant future, the system now known as IC-10X-1 will either exist as a merged black hole, radiating its final energy in gravitational waves, or as a solitary relic moving quietly through the darkness. From a vantage point within the Milky Way, observers will continue to receive its light long after these transformations have occurred, witnessing through delay the history already complete. Every photon that arrives carries the signature of processes both violent and delicate, written in the language of temperature, wavelength, and time. Through them, humanity perceives not only the details of one distant galaxy, but the deeper pattern underlying all existence energy, exchanged matter renewed, and the universe itself in perpetual motion. In this sense, the distant binary and its host stand as a microcosm of cosmic order, their brief life a mirror of the forces that govern all that is, has been, and will be. In the present epoch, the small starburst galaxy remains a site of extraordinary contrast, both a nursery and a graveyard of stars, a place where matter shifts constantly between states of light and shadow. Within it, the compact binary continues its ceaseless motion invisible to ordinary sight yet bright enough in high-energy wavelengths to mark its position unambiguously. Around this core of activity, layers of gas dust and radiation interlace, forming a luminous fabric that evolves in slow motion. Each component of this environment, from the coldest molecular cloud to the hottest plasma near the black hole, participates in a single continuum of energy transformation. It is this seamless connection between scales atomic, stellar, and galactic that defines the galaxy's character and links its transient brilliance to the universal cycle of creation. The rhythm of the binary's orbit has now been measured over decades. Its period remains remarkably stable, confirming the precision of gravitational balance between the two massive bodies. Small variations, however, continue to appear in the timing of its eclipses. These subtle shifts may record the effects of mass transfer angular momentum exchange or the cumulative influence of stellar winds. The Wolf-Rayet star, though stripped and luminous, still possesses enough mass to drive an intense outflow, and that outflow steadily reshapes both itself and its companion. Material lost from the star can either escape the system or be captured by the black hole feeding its accretion disk. When captured, it releases energy far exceeding what nuclear fusion alone could produce, making the binary one of the most efficient energy engines known. Each cycle of infall and radiation demonstrates the transformation of gravity into light with mathematical precision. Through high-resolution spectroscopy, scientists have traced the motion of the gas within the stellar wind. The results reveal a landscape of remarkable complexity: clumps, shocks, and filamentary streams moving at thousands of kilometers per second. These structures change from night to night, showing that the environment around the binary is far from static. Some of these clumps are large enough to momentarily obscure the central source, causing brief dips in brightness even outside the regular eclipses. Others collide with each other, generating local shocks that heat the gas to millions of degrees. This turbulent flow, observed through both optical and X-ray variations, demonstrates how energy moves outward in waves of alternating pressure and release. It is a living storm of plasma governed by the competing forces of radiation and gravity. The broader context of the galaxy magnifies this dynamic further. The dwarf's central regions are filled with similar phenomena on larger scales. Massive star clusters whose combined winds merge into superbubbles hundreds of light years across. These structures expand into surrounding gas, sweeping up shells of material that shine in hydrogen emission lines. The compact binary, though small, contributes to this grand architecture through its continuous high-energy output. Its X-rays penetrate the dense cores of molecular clouds, altering their chemistry and delaying their collapse. At the same time, shocks from stellar winds compress other regions, sparking new episodes of formation. Thus, the entire system operates as a self-regulating organism, where destruction and creation balance one another through the steady exchange of energy. In radio and infrared wavelengths, astronomers have begun to detect the after-effects of these processes. Filaments of heated dust outline the boundaries of old bubbles, while synchrotron emission from relativistic electrons traces the paths of past shocks. These observations confirm that the energy released by the galaxy's massive stars and by compact binaries like this one has filled the interstellar medium with magnetic fields and high-energy particles. The result is a diffuse glow extending far beyond the visible body of the galaxy, evidence that feedback from small systems can shape structures on scales far larger than themselves. What occurs within a single orbit around the black hole resonates throughout the galaxy, and what occurs in the galaxy reflects processes that define the universe as a whole. At the core of the binary, near the edge of the event horizon, matter behaves according to the laws of general relativity. Time dilates space curves, and light follows paths that appear distorted to a distant observer. Though no telescope can yet resolve this region directly, the physics is understood well enough to model its structure. The inner accretion disk glows brightest in soft X-rays, while the surrounding corona of hot plasma emits harder photons. Magnetic fields twist and reconnect, accelerating electrons to near-light speeds and launching small outflows into surrounding space. These phenomena mirror those seen in active galactic nuclei, scaled down by factors of millions, but governed by identical principles. In observing the binary, astronomers thus observe in miniature the same forces that shape the hearts of galaxies. Each photon emitted near the black hole must fight its way outward through the dense stellar wind before escaping into space. Along the way, it may scatter multiple times, losing energy or shifting direction. The spectrum observed from Earth is therefore not a simple reflection of the inner disk, but a composite record of all the interactions that occur along its path. By studying how that spectrum changes with orbital phase, scientists infer the structure and density of the intervening material. In this way, the light itself becomes a diagnostic tool revealing the invisible architecture of gas surrounding the system. The technique known as phase-resolved spectroscopy turns time into a dimension of observation, allowing space to be reconstructed from the periodic modulation of brightness. While such work refines the understanding of this particular binary, it also carries implications for a wider range of astrophysical systems. Similar processes occur in high-mass X-ray binaries scattered throughout nearby galaxies, as well as in the population of ultra-luminous X-ray sources found in more distant ones. Each represents a variation on the same theme: massive stars paired with compact objects transferring energy through accretion and wind. The galaxy that hosts this system is exceptional only in its accessibility and richness of detail. By studying it, astronomers calibrate the models that describe entire populations, linking the microphysics of a single orbit to the macroscopic evolution of galaxies across cosmic time. As new instruments extend sensitivity and resolution, the story of this binary continues to unfold. Observatories scheduled for the coming decade will capture X-ray polarization map, the distribution of gas in 3 dimensions, and trace how the surrounding nebula responds to changing radiation levels. Combined with gravitational wave detectors capable of sensing future mergers, these tools promise to unite electromagnetic and relativistic astronomy into a single framework. In that unified view, systems like this one will be seen not merely as curiosities, but as essential components of cosmic structure, bridging the domains of light and gravity. Even as technology advances, the emotional dimension of discovery remains. To detect light that began its journey millions of years ago is to look backward through time itself. The photons now striking detectors left their source before the earliest ancestors of modern humans walked the Earth. They have crossed intergalactic space undisturbed, bearing silent witness to the persistence of natural law. The constancy of their arrival demonstrates the stability of the universe's grand design, physical principles unchanging across both distance and time. In the faint signal from this remote galaxy lies confirmation that the same forces shaping the birth of stars also govern the motion of galaxies and the curvature of space. The binary, the galaxy, and the cosmos beyond all share a single grammar of energy and motion. In its light, the continuity of creation becomes visible, calm, and endless. Across the breadth of cosmic history, systems like this one form, shine, and fade in an unbroken succession. The binary that now pulses within the small irregular galaxy exists only for a brief moment compared to the age of the universe, yet within that span it encapsulates nearly every fundamental process of astrophysics: accretion, radiation, feedback, and collapse. Its light travels outward in all directions, carrying with it evidence of the mechanics that define how galaxies grow and evolve. Through it, astronomers are able to trace the continuum of creation from the smallest scales of matter falling into a gravitational well to the largest patterns of energy moving through intergalactic space. In that continuity, the system becomes both a subject and a witness of the universe's enduring order. At the level of the binary, the flow of matter remains constant, though never uniform. The Wolf-Rayet star continues to pour out gas in a supersonic wind, losing its outer layers grain by grain. The black hole, silent and compact, draws in a portion of that wind, compressing it into a hot luminous disk before consuming it completely. The rest escapes into the surrounding medium, carrying energy and enriched elements outward. The process converts gravitational attraction into radiation of astonishing efficiency, producing X-rays bright enough to outshine entire clusters of ordinary stars. Each photon released in this transformation is a particle of information about temperature, motion, and structure, offering a map of conditions otherwise invisible to direct view. Over millions of years, this steady conversion of mass into light becomes one of the principal engines shaping the galaxy's internal balance. The long-term fate of the binary has been modelled through simulations that follow its evolution from formation to final collapse. These models suggest that as the Wolf-Rayet star nears the end of its life, its wind will intensify, while its core contracts, raising both its luminosity and the mass loss rate. The orbit will gradually widen, slowing the rate of accretion and dimming the X-ray emission. Then at the end of this process, the star will collapse, producing either a neutron star or a second black hole. Should the explosion's momentum align favourably, the two compact remnants will remain gravitationally bound, beginning a new and even longer phase of evolution dominated by gravitational radiation. Over billions of years, their orbit will decay until they merge, releasing an enormous pulse of energy and gravitational waves. That final event far in the future will be brief and violent, yet it will mark the completion of the same cycle, now unfolding quietly in light. At larger scales, the galaxy surrounding this pair will continue its own transformation. The starburst phase, currently at its peak, will eventually wane as the supply of cold gas diminishes. The bright clusters will fade, replaced by fields of aging stars with cooler colours and slower lives. Supernovae will grow rarer, and the diffuse glow of ionized gas will fade into transparency. The remaining gas will settle into equilibrium, forming thin layers of neutral hydrogen and dust that drift through the galactic plane. The energy that once fueled the fierce luminosity of this dwarf will disperse into the surrounding void, leaving behind only the relics of its most active era, dense remnants, faint radio bubbles, and the quiet flicker of long-lived compact objects. In this later stage, the galaxy will resemble a fossil of its former self, its structure frozen as a record of what it once was. Yet the story does not end with fading light. The remnants of massive stars, the black holes, neutron stars, and white dwarfs will persist for eons, silently shaping the orbits of their less massive neighbours. Occasionally, interactions between these remnants will trigger new events, a collision, a merger, a brief flare of X-rays or gamma rays that once again illuminates the galaxy's dormant body. Even in quiet, the processes that define its existence never truly stop. They merely slow, awaiting new opportunities for interaction. Over still longer spans, gravitational tides within the local group may draw the galaxy toward its larger companions, stretching and distorting it, until its stars are absorbed into the halo of the Milky Way. When that happens, the black hole at its centre may continue to orbit invisible, but enduring a relic of a vanished system. To understand this trajectory is to recognize the continuity between small and vast. The dwarf galaxy, though modest in mass and size, enacts the same drama that has played out in countless others: a burst of star formation, the rise of massive stars, their collapse into black holes, and the recycling of their debris into new generations. The compact binary at its center serves as a magnified microcosm of that cycle. What happens within its orbit mirrors the processes that shape entire galaxies: the conversion of gravitational potential into radiation, the enrichment of matter through stellar death, and the slow dissipation of energy into the background of space. Through observation and theory, astronomers link the behavior of this single system to the broader evolution of cosmic structure. As data accumulates, the system's importance grows. Each observation refines models of binary evolution accretion, physics, and the role of feedback in galactic ecosystems. The consistency between what is seen and what is predicted strengthens confidence in the universality of physical law. The principles revealed by this single point of light are the same that govern quasars billions of light-years away, and the same that govern the fusion in the hearts of ordinary stars. The connection between these scales affirms that the cosmos is not a collection of isolated phenomena, but a continuous self-consistent whole. The black hole, though infinitely compact, participates fully in that unity. For all its complexity, the story told by this binary is simple at its core. Matter drawn by gravity falls inward. In falling, it releases energy. That energy radiates outward, altering its surroundings and eventually dissipating into space. Over time, the same material may fall again elsewhere, repeating the process under different conditions. It is a cycle without beginning or end, one that converts the potential of structure into the experience of light. In the dwarf galaxy where this system resides, that principle unfolds in real time, visible through the constant pulse of X-rays, marking the motion of two invisible bodies. What began as gas collapsing in darkness has become a beacon whose light now crosses intergalactic space, reaching observers on a distant world orbiting another star. When viewed in this way, the binary transcends its identity as a single object. It becomes part of the long narrative of transformation that defines the universe. Its flicker is a single note in an endless cosmic rhythm, a quiet proof that energy and matter remain forever intertwined. Long after its light has faded, the elements it helped disperse will form new stars, new planets, and perhaps new observers to study them. Thus, even its eventual disappearance ensures continuity, binding its brief existence to everything that follows. The galaxy itself may vanish into the larger structures of the local group, but the laws it obeys will endure unbroken and exact. In this enduring symmetry lies the quiet grandeur of the universe, not permanence, but persistence, the ceaseless motion of matter toward balance, the unending exchange between darkness and light.